Now we are seeing analysis of temperature stresses in composite bars. Let us take a composite bar which is made by two materials, 1 and 2, and which is fixed on left side and also which is joined rigidly on the right side. So if we give the heat input or if we increase the temperature, so because of rise in temperature, the two bars will expand same amount because we have fixed left and right, and here it is fixed and here it is joined, both ends are joined such that it can expand on the right side. So suppose let us take that this right hand side of this composite bar is free, means this is these two ends are not joined. So in that case, because of a rise in temperature, the bar 1 and bar 2 will expand independently. So let us take the coefficient of thermal expansion for bar 2, that is alpha 2, is more than alpha 1, that is coefficient of thermal expansion of bar 1. So we are taking alpha 2 more than alpha 1. So in that case, the bar 2 will expand more than the bar 1. So uh, in that process means here, so let us take this free expansion of bar 1, that is delta L1, is given by the formula L alpha 1 into delta T, where L is the length of bar 1 and alpha 1 is the coefficient of thermal expansion I told, and delta T is the rise in temperature. So this is the free expansion of bar 1. So in the same way, we can write free expansion of bar 2, that is delta L2, as L into alpha 2 into delta T. So here initially we have taken the two lengths of bars as same, and that is nothing but length of the composite bar. So here but because this actually these two ends are joined rigidly, so in that process, so when it is free, means with two ends are not joined, the bar 2 will have more extension, that is delta L2 is more than the delta L1. So but because actually these two are joined rigidly, so this bar 2 will apply a tensile load on this bar 1, and such that this bar 1 will have expansion, more expansion by an amount of x1, and in the same way this bar 1 will apply a compressive load on this bar 2 such that it will have less expansion, means less free expansion, and the amount is less by x2. So if you observe, the load applied, means the tensile load applied on bar 1 must be equals to the compressive load applied on bar 2. So why? Because here in the actual situation, both the ends of bars are rigidly connected such that when we increase the temperature of this composite bar, both should have same expansion. So to get that, this will have an extension of extra extension of x1, and this will have less extension by the amount of x2. So this bar 2 will apply tensile load on bar 1, and bar 1 will apply compressive load on bar 2. So anyway, the tensile load applied on bar 1 is equals to compressive load applied on bar 2. So we can write an equation here, uh, that is tensile load applied on bar 1 is equals to compressive load applied on bar 2. So P1 is equals to P2. So we can write P1 as sigma 1 A1. Why? Because we know from the simple stress definition or formula, stress is equals to load by area, or we can write load is equals to stress into area. So P1 if you write, we can write sigma 1 A1, and if you write P2 it is sigma 2 A2. Let us take this as equation number 1. And here if you observe from the diagram, To get the same extension of bar 1 and bar 2, the composite total composite bar. So when you observe this diagram, from this diagram we can say delta L1 plus x1 must be equals to delta L2 minus x2. So from that we can write equation as delta L1 plus x1 is equals to delta L2 minus x2, and I told delta L1 is the free expansion of bar 1. So that is given by the formula L alpha 1 delta T, and delta L2 is a free expansion of bar 2, that is L alpha 2 into delta T. So friends, if we require more clarification on this formula, please refer my previous video on temperature stresses or thermal stresses. So here we can write these formulas for free expansion of bar 1 and bar 2, and if you read, we have already written the equation. So delta L1 plus x1 is equals to delta L2 minus x2. So L alpha 1 into delta T plus x1 is equals to L into alpha 2 into delta T minus x2. And here x1 is the extension or increase in length of bar 1 because of the tensile load applied on bar 1. So this we can write as extension increase in length of bar 1, we can write sigma 1 by E1 into L1 or L. So why? Because we have taken L1 is equals to L2 is equals to L, that is length of the composite bar. So we can write simply write it is L. So here friends, see how we can write this extension as sigma 1 E1 L. So this we can write from the simple basic formulas. So we know Young's modulus is equals to stress by strain, or strain is equals to stress by Young's modulus, and strain in the lengthwise direction we can write delta L by L, and delta L is equals to stress by Young's modulus into L, that is sigma by E into L. So we are writing here delta L1, that is nothing but x1. So we are writing x1 here, it is sigma 1 E1 L1 or simply L. So in the similarly we can write the decrease in length x2 of bar 2 as sigma 2 by E2 into L2 or simply L. So here sigma 2 is the compressive stress, sigma 1 is the tensile stress, because on the bar 1 tensile load is acting and bar 2 compressive load is acting. So sigma 1 is the tensile stress, sigma 2 is the compressive stress, such that we will get x1 as the extension and x2 is the decrease in length of bar 2. So if we write x1 and x2 like this, and if we simplify, if you put in this formula, so that is L L1 into alpha L into alpha 1 into delta T plus, in the place of x1 we are writing sigma 1 by E1 into L is equals to L into alpha 2 into delta T minus, in the place of x2 we are writing sigma 2 by E2 into L. So if we rearrange the terms here, means sending this term to the left side and this term to the right side, so we can write here sigma 1 by E1 into L plus sigma 2 by E2 into L is equals to L alpha 2 delta T minus L alpha 1 delta T. So here in this L is common on the left side and right side, so we can take out common and we can cancel, and the remaining equation we can write as sigma 1 by E1 plus sigma 2 by E2, and delta LT is common here, so we can take it common, and into alpha 2 minus alpha 1. So this take it as equation number 2. So from these two equations, means from this first equation, that is sigma 1 A1 is equals to sigma 2 A2, and from this second equation we can find temperature stresses, that is sigma 1 and sigma 2 in composite bars. So friends, for more videos please subscribe and activate bell symbol. Please like it, share it with your friends, and don't forget to subscribe. Thanks for watching.